Now in this next video we're going to take what we just learned and apply it to binomial probability for Mendel, or basically for genetic crosses. But one thing I want to touch base on is, which I didn't do in the last video, just as a reminder, if we have a family of 7 children and 3 of them are girls, the probability of calculating that can be given with using the following variables: n, where we say this is equal to the number of trials, in this case, is equal to 7, okay? And then x, which is the number of successes, in this case the number of girls, which is equal to 3, okay? And then of course p, which is equal to a half, which is the probability of girl, and then q, would be 1 minus a half, okay? So to calculate that, I gave you a little bit of a formula, and the way that that formula worked is it basically counted all the ways in which you can get 3 girls, giving this part of the equation. This is sort of the number of ways, and that was given with n factorial, okay, n minus x factorial, okay, x factorial. So number of trials minus the successes factorial, number of successes, and then this is the probability of any given way. Probability of any given way, and in this particular case with boys and girls, p in the general form, the x, 1 minus p to the n minus x. Okay, so if there's 3 girls, then there have to be 7 minus 3, 4 boys, of course. So just filling this in, we get 7 factorial, 7 minus 3 factorial, 3 factorial, okay, and then 1/2 to the third times 1/2 to the fourth. And the simplification that I didn't do in the last one, which I'm going to actually just demonstrate for your purposes, this can be sort of just obviously indicated as 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial, so 4 times 3 times 2 times 1, okay, times 3 factorial, okay, 3 times 2 times 1. Now, just as a purpose here, this is actually easier than it looks to calculate because all these ones cancel out. This one, this one, this one, of course the ones would cancel out. And then likewise, if you see there's a 6 here, then this 3 and 2 will cancel out. So, okay, so this is actually 7 times 5. So it turns out there are 35 ways in a family of 7 children for there to be 3 girls, and the probability of any particular set of 3 girls is a half to the 7th power. Okay, so that's all well and good, but what we want to know is, how does this apply to genetics? Now, in the case of Mendel's peas, we can think of the round or wrinkled peas. Now, in this particular case, reminding you of the Punnett square to indicate the way in which we calculate the probability of any particular pea from a cross between a big R, little r plant and a big R, little r plant, reminding you that these individuals, okay, or these individuals give wild type or round peas, and these individuals give the wrinkled pea, okay, because it's recessive. So in this particular cross, okay, reminding you how this would work in the Punnett square framework, okay, oftentimes what we do is we do this Punnett square, and one thing that's often forgotten is in the Punnett square is what you're indicating are sort of the 2 different ways in which, or the multiple different ways in which you get fertilization events from the male germline of the plant or an animal and the female germline, okay? What type of pollen, what type of eggs are being transmitted, okay? Well, from a mother who has this particular genotype, as we know in meiosis, you either transmit the big R allele or the little r allele in your gametes, and so the probability of either of these ones is a half, okay? Likewise, the probability transmitted through pollen of big R allele is equal to a half, okay? And a little r allele is equal to a half, okay? And so all the Punnett square really is just a representation of how you can multiply probabilities, because the chance of gamete coming from a female having a particular genotype is considered independent from the genotype of the pollen that it fertilizes. So to calculate these particular genotypes, which are possible, okay, of course, like that, what we're doing is we're multiplying, and this square is a sort of a visual representation of these multiplying independent probabilities, because this is equal to a half times a half, right? The chance that you get this allele and you get that allele, okay, which now, of course, is equal to a quarter of this grid. So just to remind you here, then, you know, this is a half times a half, so on and so forth. This is basic stuff. But the point here is that we're dealing with a situation not in which the probabilities of, like, such as in the case of a boy or girl, is 50-50. Now, the chance of being round, okay, well, you sum up the mutually exclusive probabilities. So this is equal to a quarter, this is equal to a quarter, this is equal to a quarter, okay? So that's where the 3/4 comes from, is because you're actually adding these mutually exclusive scenarios. And these are mutually exclusive because this means that the little r allele came from dad, whereas this means that the little r allele came from mom, or the female germline. Okay. So you sum those up, a quarter plus a quarter plus a quarter is the probability of a round p-bearing plant, of course, is equal to 3/4, and then, of course, then the probability of a wrinkled p-bearing plant, probability wrinkled, is equal to a quarter. Now, the reason I reiterate this is because I want to show now something more complicated in which you can say, what is the probability of a plant bearing a set of progeny, say, for example, that are all round p-bearing plants? Okay, well, that's obviously just similar analogous to the boys and girls case. Suppose that there are 7 plants in the progeny. What types of p's do they bear? Okay, well, to calculate the probability that, you know, all 7 are round p-bearing. Okay, well, just as before. Okay, but now it's 3/4. Okay, to the 7th power. Okay. Now, if you were, say, for example, all wrinkled, it would be, of course, 1/4 to the 7th. Now, those are easy ones to do, but let's actually ask something similar. Let's say, what is the probability of, in a set of 7 offspring, that 3 are round p-bearing plants? Okay, therefore 4 are wrinkled. Okay, so what is this? Well, you know, of 7. Well, what we do is we just do what we did before. There's 7 progeny, and we talk about the number of trials, so we would say that's equal to 7 factorial. Okay, 3 are round p-bearing. Okay, so you'd say 3 factorial, and then 7 minus 3 factorial, which is what we've done before. Okay, but now what we've done differently is now p is different. Okay, so p is equal to the round p-bearing, and we're going to say that's equal to 3/4, and q is equal to 1/4, okay, of course, which is also equal to 1 minus p, okay? So in this particular case, it's 3/4, okay, to the 3rd power, okay, 1/4 to the 4th power, okay? So this is a way of calculating any particular combination. For example, if you have 74 progeny, what's the probability that exactly, say, for example, 17 are round p-bearing and the remainder are wrinkled p? Now, obviously, that's going to be a low probability, but this is a way of calculating this exact probability using the same formula that we use for boys and girls.